Right. The next thing that we are going to concentrate is the AVR internal architecture. Now, as you can see in the figure, this architecture is using Harvard architecture, if you do remember from lecture 1, where we have got a separate bus for program memory and separate bus for internal RAM, EEPROM, timers, and interrupts and ports and so on. So CPU is sitting in between. We have got the oscillator, we have got the program ROM memory, and some other resources around it. Now, we are going to see in details how these are seen inside of the architecture of an Atmega 128. Now, Atmega 128 is a low power 8-bit 16 megahertz microcontroller. It's a RISC architecture, which I'm going to talk about that later on. And they are mostly single cycle instructions, which we are going to talk about those as well. And they are a single 16-bit format. So what do we have inside of the Atmega 128? We have got 128K flash program memory, which we put all our codes in there. 4K EEPROM and 4K internal SRAM. So internal SRAM, which I'm going to talk in a bit, the details of it, is quite useful when we are talking about the ALU instructions and performing some operations over there. Now, inside of it, we also have 32 by 8-bit register file. Now, what is that register file? That register file is, as you can see, has an access to ALU. Now, if you want to perform any arithmetic or logical operations, we are doing those through the registers over here. So in total, we have got 32 registers, 32 rows, and each of those are 8 bits. So as this is an 8-bit architecture, we can have an 8-bit data stored in those registers. If you want to store 16 bits or 32 bits, you have to separate the data into number of registers. Now, another important thing over here, ALU can use this directly and by fetching the data from there, doing some operations and restoring it over there. 6 of the 32 of these registers, starting from R26 to R31, they can be a pairs. So if you want to have create a 16-bit register, you can have R26, R27, R28, R29, or R30, R31 as a pair that you can store a 16-bit data into it. Status register. Status and control register is also important when you're performing some operations related in the ALU, like arithmetic or logical unit operations. You might have a 0, you might have a negative or overflow. They are all shown in the status register. So it's actually a flags that they can be raised depending on the situation or the outcome of the results. And of course, we have got some special and peripheral features, the interact unit, SPI, serial port, watchdog timers, which is an external timer that can be used automatically to detect software anomalies, but we are not going to see that in this course. Analog comparator, when you have an analog inputs, you can compare them, and of course, input-output modules that we can interact with outside world. So this is in general what we have got as an architectural overview. Now, what is more important is how this AVR CPU is working, because that's the brain, and like we have said in the first lecture, that's the boss. Okay, CPU is the boss, and we have to understand how CPU of AVR is working, because everything is running over there, and we have to know how these things are running around it. So what we need to know about AVR CPU. So CPU, they use many registers to store data temporarily. So in this case, R0 to R31, 32 register. And in order to program in assembly language, we must understand the registers. Okay, so that's why we are going to see them in details. And we also need to understand the architecture of a given CPU, like this one, and the role they play in processing data. Okay, so we have got ALU, we have got program counter, temporary registers, instruction decoder, and status register over here. Okay, so these are some of the important logic blocks inside of our CPU that take care of all the fetch, decode, execute cycles. And generally, AVR microcontrollers have main registers for arithmetic and logical operations. And in CPU, registers are used to store information temporarily. So if you want to store it for permanently, you have to store it outside of the CPU in one of the memories that is placed or connected to the CPU. So what we can hold as an information, it could be a byte of data to be processed or an address pointing to the data to be fetched. And as we already said, the majority of the AVR registers are 8-bit. So we are using 8-bit architecture. We have got an 8-bit registers. And like we have said, in the AVR, there are 32 general purpose registers, which we call them GPR. As the name suggests, GPR, and they are from R0 to R31 and located in the lowest location of memory address, which we are going to see in a minute. Now, before we get into the details, I want to show some simple instructions that we use in AVRs, like to deal with these GPR and ALU itself. So the one important instruction that we are going to see is LDI. So what is LDI? Now LDI stands for load data immediate. Okay, so in order to load data immediately into the GPR, we are using LDI instruction. So we can say that LDI copies 8-bit data into the GPR. So it's like defining a constant. So the format of it is like LDI RD K. Now, one of the important thing over here, this is a typical AVR instruction. If you want to write a comment, we use, let's use different color. We use semicolons. So load RD, which we call it destination register, with immediate value K. Okay, so immediate value is a constant value. And few properties over here. They must be, this is a characteristic of AVR between R16, R31. So if you are going to use LDI instruction, we can only use the registers from R16 to R31. We cannot initialize a constant between R0 to R15. You can use it for any other instructions, but for defining a constant, the lowest register that you can use is R16, the highest is R31. And K K is what? K is an 8-bit value. That can be 0 to 255 that we can store. Or we can say 0, 0 to FF in hex. This is decimal. Okay? And from R16 to R31, we can define an 8-bit constant. Let's see an example. We can say LDI R20 0 hex 25. Now, what does that mean? Normally we write the comments next to it, but as I don't have a space, I'm writing underneath. Load R20 with 0 hex 25. This means in hex, okay? And this is actually means, in other words, R20 is 0 hex 25. Okay, so this is how we can use LDI instruction. And you can see over here as well, LDI R1653. You can define a decimal. LDI R19 132, LDI R23 hex 27. So it can be in any format, but it has to be a constant. So there are some rules about AVR programming that we need to be really careful. First of those is if you want to present a number in hex, we put a $sign or 0 hex in front of it. Now, if you don't put anything in front of a number, then it's a decimal. So we can say this is hex, decimal, we don't put anything. So $25 or hex 33. But decimal, you can just write 25 or 33. Okay, so you have to be careful over here on what you want to define. Another rule, now, if the values 0 to F are moved into an 8-bit register, such as GPRs, the rest of the bits are assumed to be all zeros. What do we mean by that? Let's say I have got LDI R16 0 hex 5. Now this is actually what? This is actually R16 equals 0 hex 05. So as we don't have it over there, it doesn't mean that it is just 5 because you have an 8-bit register, you have to fill it. Okay, so R16 is going to be first 4 zeros and then 0101. Okay, so this is how we are representing inside of the register. And the third and the last rule, while we are programming AVR, if you have a larger value than 255, which is an 8-bit, or FF in hex, it will cause an error. So, for example, you cannot say LDI R17 0 hex 7F2. It's illegal because you have got 4, 8, 12 bits over here, which is 12 bits are greater than 8 bits, which we cannot store them. Okay, so that's not possible. Okay, so this is the first instruction that we have to learn to define the constant. Now, next thing that we are going to look at is the arithmetic calculations. So before we get into the arithmetic calculations, I want to redraw this AVR's architecture, part of it, so that we can make sure that we understand how the ALU is performing these calculations. So what we have got is 32 by 8 GPR, okay? And then we have got ALU, and the GPRs are directly connected to the ALU for faster operation. And the output of the ALU can go back into the GPR. It can be restored over there. These are all 8 bits. And on the other side, we have got status register. Now, the output of ALU can raise a flag, which we have got half carry, sign, overflow, negative, 0, carry. We have got all these flags in the status register. And then, of course, the carry bit. That we need to take care. So now, once we understand this architecture, because we have got set of drawers over here in GPR, we can fetch the data, perform the operation, and store it back into the GPR. Now, the instructions that we have got, the first one is add instruction. This is a typical operation that we perform. Now, add instruction has got add, again, destination register, and also another GPR register that we perform the operation. So how do we read this? We read it as add RR to RD and store the result in RD. Okay, so RR is added to the RD and the result will be stored in there. In other words, I can say RD equals RD plus RR. This is the operation that ALU is performing. Okay, so it's getting RD and RR, adding them together and storing it in RD. Okay, so this is how it looks like as well in the lecture notes. Add R25, R9 to R25, add R30 to R17. You can add different registers over there. As you can see, we can use any of the GPRs. There's no restriction over here. Okay, so let's do a simple example. Add two numbers such as hex 25 and hex 34. Now, first, we have to define these constants before we do any add operation, because you cannot just directly do add a constant. Okay? There's other instructions over there, which we are going to see later on. So LDI R16, we have to define it 0 hex 25. And then, so R16 has got hex 25, LDI, R17 will have hex 34. Okay, so we defined two constants. Then we can have an add operation. Depends on where we want to store it. Let's store it in R16. That is going to be R16, R17. So if we write the comments, this is going to be like R16 equals hex 25, R17 equals hex 34, and this one is R16 equals R16 plus R17. That's going to be the content of it, okay? We are not adding the registers, we are adding the contents of the register. So we can say that R16 is going to be 0 hex 59 because of, or let's do it this way, 0 hex 25 plus 0 hex 34, which is equal to 0 hex 59. Okay, so that's what that means. Another example, write a program that calculates 19 plus 95. Now, we can say LDI R16, oops, 19, LDI R17, 95, and then add R16, R17. Okay, so we can easily do that, and we will get the value of 19 plus 95. This is a decimal, be careful. It's not a X. You can use different registers apart from R16, R17. You can use 20, 21, 22, whatever you want. And you can perform the operation. How about 19 plus 95 plus 5? Now, there are two ways of doing this, actually. It's not actually two ways, but there are efficient way of doing this and inefficient way of doing this. So method one is, I can say LDI R20, it's going to be 19. LDI R21, it's going to be 95. LDI R22, it's going to be 5. I define all the constants, and then I do add R20, R21, and then I do add R20, R22. I store everything in R20. Okay, this is one way of doing this. The second way of doing this, if you are desperate about the registers that you have got, that you have to use a lot of those, and you have a limited left, what you can do is you can say LDI R20, 19, LDI R21, 95. Then what we can do is we perform the operation add R20, R21. Then I define the new value R20 into R21 because I use that value, and then I define 5. And I just do another add operation by saying R20, R21. So rather than using 3 different registers, I just use 2 different registers. So if you are limited with the number of registers, then you can do this method. Subtraction is also similar to addition. There's nothing different over there. And you can do RD minus RS. So RS is going to be subtracted from RD, and the value will be stored in RD. So R25, sub R25, R9, R9 will be subtracted from R25, and then the value will be stored in R25. And it's exactly the same as the add function. Another arithmetic operation is increment, adding 1. So there's an instruction called inc the register. So you are not actually incrementing the register address, you're incrementing the content of the address. So increment RD means RD is equals RD plus 1. So if you have 5 over here, then it's going to be 5 plus 1. If you have 10 over here, then it's going to be 10 plus 1. That will be 11. Or if you want to decrement it, then 10 minus 1, and so on. So these are all can be used in simple instructions.